And we are live. So I'll just wait a couple of seconds. Also, do let me know when people start showing up.
Yeah, they are, but we can wait for a while.
Cool.
I see people coming in.
Thanks.
Yeah, let's start.
So first of all, welcome to the Academy. We are very excited to see you join us. And we are very excited that you took this first step on your learning journey. And welcome to our live learning session where we will be going through some interesting yet fundamental topics on OpenCV and deep learning. I'm Ritik, a machine learning engineer at PyMS Search, and we have with us two members from the PyMS Search developer team, Audithro and Dev. So Audithro and Dev, say hello.
Hey, everyone.
Very
Before we
excited
move,
to be here.
right. So before we move forward with the lesson, I just want to make something clear to everyone present. We want you to ask as many questions as you feel like. We will be keeping an eye on the discussions tab or on the comments tab, and we'll be trying to answer them as we move forward. So go ahead and post all your queries in the comment section. We will be taking them up and answering them as we go forward. And now for the actual topics of this live session. So we chose these three very specific topics to go together. And by the end of the session, we do have a surprise plan for you. So do keep that in mind and do hang on or stay tuned till the end of the session for the actual surprise. And this is a small summary of what we will be covering today. We'll first demonstrate how to build a virtual environment. Then we'll learn about OpenCV histograms and histogram equalization. And then we'll dive into something called squeeze excitation network, which is simple to understand, but mind-bendingly effective in practice. And if you ever feel like these topics are a bit advanced or difficult to grasp on the first try, do not worry. Just try to enjoy the session and take the discussions in passively. And as you go through the academy on your own time and at your own pace, these will make much more sense and you will be able to connect the dots even better.
Right. On top of what Ritvik has said, I'm sorry, Ritvik, to take away what you were saying.
Sure.
On top of what Ritvik has said, I want all of you to understand that these are sampled from our academy that you have purchased. And these are in order of how you are going to go into the academy. So creating a virtual environment is something which is very basic, but very fundamental to everybody. OpenCV histograms is a little intermediate. Don't get overwhelmed. And squeeze excitation networks are a little advanced. So we just wanted to sprinkle some of the things that you will eventually get to, and and these are on the entire spectrum of the academy. So keep that in mind. Don't get overwhelmed. Start asking questions. Keep forming the dots, and we will, as in PyMed Search, will help you bridge the dots. So that was something which I wanted to say.
Right. So so we'll be going ahead with our first topic right now, which is creating a virtual environment. And as Audithro mentioned, this is an essential skill for any Python developer. It will basically help you keep your development environments clean and segregated. It will also allow you to maintain your sanity when you work on complex projects with many dependencies and on very specific versions of libraries. Uh, these are the actual set of commands that we will be needing to create our virtual environment, and we'll be explaining them as we go along. So don't get afraid or bogged down with with like code jargon on the screen, and also do not feel pressured to take note or jot everything down. because we will provide you with the links to the relevant tutorials as soon as this session is over. We'll be actually, posting them in the description of the YouTube live stream that you're watching right now. And like, I'll just stop sharing for a moment here and spin up a virtual environment to show you how to create a virtual environment from scratch and how you can make use of it. But before I do that, let me ask you guys, Arthur and Dev, have you ever had an instance when a virtual environment or the lack of it messed up your development routine?
I think this question is for Dev. It's not for me. So Dev, you can take it away.
So I feel you guys had like pre-planned this question just for me. So yeah, during my starting days as a machine learning enthusiast, I did not take the concept of containers and environment seriously. And
Right.
what it ended up doing was absolutely ruin my dependencies, ruin my packages, and the term basically it basically tripwired my whole environment. Like one wrong pip install and it was just gone. That like 3 hours of my whole life just lost. So it's this environment containers. This is actually very important, as you will soon learn. So do not take this lightly.
Right. And
Right.
on top
So,
of and on top
sure.
of that,
Right.
Ritvik, uh, so while talking to Dev about his tripwired local system, I also got to know that he has an analogy for virtual environments. He considers them to be rooms in houses. So Dev, would you want to elaborate on that, because that was a really great
Yes.
analogy.
So how I see environments are like, consider your house, for example. You have a
Right.
dining room, you have a
Mm-hmm.
bedroom. So you will not sleep in your dining room, right? The dining room
Right.
is there for a
Right.
specific purpose, and the bedroom is there for another specific purpose, and
Mm-hmm.
they two do not interact with each other. So environments are kind of like that. They're isolated containers, or if you want a even greater or even on a bigger scale, then I would call them isolated universes, which have no
Mm-hmm.
idea that they don't have any idea for each other's existence, and they each are there for
Yeah.
some specific purpose that you want. You are basically the architect in those rooms, and it's up to you to how you will utilize them, but
Right.
they do not interact with each other. That's how I see environments essentially.
Right. It was a great analogy. So I just wanted to pitch that in. Yeah, Ritvik, you were saying.
So yeah, that is a great analogy, and like, it really helps in understanding that why you need specific for environments. Like, if you think about rooms
Exactly.
in your house, your house is your machine or your computer, you do need rooms because you keep separate things in them or do separate things in each of those rooms. You wouldn't be dining in your bedroom or going to the bathroom in your living room. So those are very specific requirements. And similar to that, you will have when you work on actually complex projects, and even projects that you will find inside OpenCV and Deep Learning Academy, you will be needing to create separate virtual environments just so that your libraries do not, as they've mentioned, get tripwired. So as they've mentioned, I will be spinning up a room. I'll be sharing my screen. But so Arithro, do we actually have any questions or any
I don't
comments?
see any. No, I don't see any questions at this moment. It's very early at the stage, so I don't think people are posting in
Sure.
questions. But I'll keep a look at the
Yeah.
chat.
So, guys, like, if you're watching this, please do post your questions in the chats, or if you
Right.
have something that you want us to, discuss on these topics, then please post them in the chat, and we are actually keeping an eye open so that we can answer your questions. And
That I
now
is me
back.
basically.
Yes, that I is Arithro. And so what we are going to do right now is create a virtual machine on our cloud instance called Jarvis Labs. If you have, if you are a Pioneer Search reader or you do follow our blogs, and since you have taken OpenCV and Deep Learning Academy, you might just be following them. So like, you will have come across the term Jarvis Labs. Jarvis Labs is is a cloud instance provider. It provides us with the flexibility of creating virtual machines on cloud. Do not get afraid that, or do not think that you need this particular you need Jarvis Labs, or you need an instance from Jarvis Labs to actually create a virtual environment. You do not need that. We are just showing this on Jarvis Labs for ease of understanding, but these steps will essentially be the same for your machine or your computer. And if you do have a specific OS version, we actually have a lot of tutorials on installing OpenCV on your machine on all of the popular operating systems. So we'll be linking them, and you will find your relevant resources there. So please don't be worried about this. So I'll just go ahead and launch a virtual machine. Takes a little bit of time.
And just to plug about Jarvis Labs, they are insane. It's an insane company providing like insane GPUs at a very cheap cost, and they have been helping us with our experiments, as in PyMed Search with our experiments. So we would want you all to check them out. And yeah, so it does take some time, but Ritvik, just to question, like keep the discussion flowing. What are we using? Like, do we use a GPU now? Do we use a CPU now? What is the instance that you just pulled up?
No, we would actually need a GPU for our deep learning projects or our
Right.
projects involved in TensorFlow. But right now, what we are doing is creating a virtual environment on a CPU instance.
Mm-hmm.
And the reason we are doing that is because this is just for demonstration purpose, and we do not need a lot of compute, which is what GPU provides for us to create a virtual environment and then start working on it.
Got it.
So I'll just go ahead and start this. I'll go to the terminal.
By the way,
And-
guys, just one thing though.
Yeah.
To our viewers, everything Aditya said, everything Ritik said, Jarvis Labs is great. And let's be honest, anything that is named after Iron Man's AI companion can't be that bad, can it?
True.
Right. So we'll be actually typing in the comments that you saw in the Google Slides a while back. And again, do not be afraid, or do not start taking notes. The point of this whole session is to show you how easy it is to create a virtual environment and start working on it. It is not to make you feel that these are really essential steps, and you will find these mentioned in our tutorials as well. So just a second there. Is my screen a little better visible?
Yep.
Right. So that.
So with touch, you're basically building the .bash RC file, right?
Yes, I'm building the .bash RC file if it does not exist yet, and then I will be opening it, and then I will paste a bunch of computer jargon or commands that will essentially allow us to use a very specific library that we are going to install later on. So these are the commands that will let us use that library. And that library is called virtual env or virtual env and virtual env wrapper. So what this does is, going back to Dev's analogy a while back, virtual env and virtual env wrapper are the actual brick and mortar that builds the rooms inside the houses, right? And it helps us create the virtual environments or the rooms that we need in our local system. So we have pasted in the commands that we needed, and now we need to save it. Control X to do Control X to do that, and then Y and enter. So we have just pasted in the commands that will allow us to access the libraries. And now we need the actual library or the virtual env and virtual env wrapper libraries that we will be using to create the virtual environments. So to do that, we will be using our friend pip install the name of the library, virtual env, and virtual env wrapper, and then press enter.
And what is that .bashrc file which you just created and put a lot of computer jargons in? What does it do?
Yeah, so think of it like this: that your system, or
Mm-hmm.
your basically your operating system, needs to have a control center, a hive mind that
Right.
controls every configuration and system commands, and that this is that file that actually allows you to tweak those system commands, or control those configurations.
Right.
So that
Makes sense.
the reason we are pasting those commands inside bash rc is because we want our system to recognize virtual env and virtual env wrapper once they are installed, and once it
Mm-hmm.
recognizes, we can basically you know use it as we need. So before we actually go ahead and use it, we need to activate it, and to do that, we'll paste this simple command, source bash rc, and I think this is correct. So I'll just go ahead and remove all of the commands that have been like all of the output from the screen, and control L to do that. And then I'll create a virtual environment. So the command to do create a virtual environment is mk virtual env without any space. And then I will give the name of the actual virtual environment. So here we are just using CV, shortened abbreviations for computer vision. And then we'll do something interesting. We will mention the version of Python. So a lot of times in your development journey, you will actually come across libraries that use Python 2.7 or 2.8 or very specific versions of Python. We really hope that you do not, uh, but it does happen,
Yeah,
and
it does happen.
it will, like, if you, so basically, that is notorious to debug. If you
Mm-hmm.
have Python 3 and then a very specific library needs Python 2.7, it's it's almost impossible to recognize the output and then debug that, okay, this is this very specific library I need to install. So a good practice is to have your virtual environments have a Python version mentioned or specified for your virtual environments. This is not required. This is not absolutely required to create a virtual environment, but it's a good practice and one that we recommend very much. So this is a command to create the virtual environment. It will probably take a few seconds. See, and now, if you go ahead and look at this, what this tells us, what this little CV inside these parentheses before the root directory tells us, is that now we are working in the room that we have just created. We are working in the virtual environment of CV. And if we want to work on a version of Python, or if we want to create a Python file, or download a Python file and start working on it, that will actually be of this specific version. And the way we can check that is by typing which Python or which pip, and you can see that it says user local bin, and then virtual environments, virtual envs, and then cv, which means that this is the specific virtual environment that we just created, and that is something that is what we are working on. So
Mm-hmm.
that basically brings us to the end of creating a virtual environment. And you saw how, like, because we actually took the time to explain, it probably took 5 minutes, but it is probably a 1 or 2 minute thing, and it takes so little time, but it saves you so much of pain and time and headache later on. So we really recommend that you do this. We really recommend that when you get our code, or when you start working on our code, you download them and create your own virtual environment and start working on them for each of the projects that you do. And what this is going to do is create a habit inside you, which will allow you to work on complex scalable projects later on when you are in the industry, or research, or academia, or Google maybe. and then you will probably not have to worry about things like tripwiring your virtual environment. So with
Looking at
that,
you, Jyoti.
yeah, with that, we will actually close this, and I will stop sharing my screen for a second here, and I will throw it over to Aritro again. So Aritro, do we see any questions or comments, and am I actually audible, guys? Is is everything that I'm saying, is it like an echo chamber that only we are talking?
Okay, so there are three questions that I saw from you alone. One is whether there are questions on the chat. There are not as of yet.
Right,
Two is you are very much audible and visible. And
right,
the analogies that Dave, you, and I have presented do make sense. So don't worry about that.
right. So again,
And we
guys,
also have a comment from a user. He says yes to your questions. So,
wow, thank you,
so you are. So
thank you,
you are audible and visible.
thank you. And
So,
if you are,
sorry,
yeah,
you go
Dev.
ahead.
No,
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 no, please
please.
go ahead. No, I
Yeah,
was just
so
going to make. Okay. Please, Ritik, go ahead.
Yes.
I was just saying that if you are watching this and you do come across something that is, not clear at the first try, please
Mhm.
post your question and we will be trying to answer it. Like we will be answering it basically as we go forward, because we want this session not to be amongst ourselves, but to be with you guys for whom this session is. We want it to be as interactive as possible so that you get to, learn or take away something really useful from this.
Or maybe
Uh,
we could take away from
Yeah.
really
yeah,
useful
both
from
ways.
somebody.
Which
Exactly.
is what I was going to say. That this is something that I just realized as you guys have made me the analogy king. Going back to the the universe as containers analogy, that
Hmm.
Orithra and Ruthik, do you not think that since we can specify the Python version for each our containers,
Right.
it's like we are one of the universes we are giving Python 3.7, the latest, that's to 2022. Other we can just give Python 2. That's like we're traveling back in time to 2000, I don't know, 10 or something like that. So
Yes.
that
Yes,
kind
it
of
is.
that's fun.
Yes, it is. And for libraries that have not been, updated for the last 10 years, you probably do need to go back in time and do that.
Yeah.
Oh
But
yeah, that's
that's
Multiverse
so
of
common.
madness, if you may.
So I'll just share my screen again, and do let me know if it is visible.
Yep, it is very much visible.
So we have actually created a virtual environment, and we did it on a virtual machine, but now we are going to be going into the actual, you know, uh, the actual juicy parts of this session. And remember that from here on now, these these concepts will be accompanied with code that we will be going through together to better understand them. And if you feel anywhere that this code is something that you are not familiar with, or you do not have the bandwidth to understand right now, we encourage you not to pause or skip this session, because it is important to take in information even if you feel like that's a little bit higher from your standard right now. Because what that will allow you to do is then later on go back as you go through the OpenCV and Deep Learning Academy, you will understand or you will pick up core concepts from OpenCV and deep learning, and you will be able to understand these concepts a little better. And then when you join those dots back actively by yourself, they will mean much more. So we will be providing you with the collab notebooks in the description. We will also be providing you with the tutorial links. But I highly encourage you to not skip the session or not pause and watch it on a later date. One, because that will suppress your habit of learning passively, even if it's like this. And two, because we do have a surprise planned for you and you will be missing that. So on to our next topic, which is histogram and histogram equalization using OpenCV and Python. So this like, I'll just be brief here. This image on the left, so is my mouse cursor visible? And I am also looking at the audience, so it will be great if you could post that if this is visible, if I should zoom in or something like that. So this image on the left hand side, the black and white image, has this histogram, and we actually need to understand what histogram means before we go on to histogram equalization and how we are going to do it. So what this if you are watching this, you're probably looking at a little bit pixelated image, like it's just so slightly pixelated, right? And the reason it's pixelated is because it had a certain dimensions. The image was of x plus y shape or size, and then when we put it in this slide, it got stretched to x plus h and y plus w shape, right? It got stretched. So basically, the pixels inside the images are now occupying a little bit higher space than they are made to. Does that make sense? Is that
Right.
analogy useful? Right.
Yeah. So does that mean, I'm just reiterating, does that mean that it's supposed to take some pixel per inch, but now it's taking a little bigger pixel per inch of the screen?
Yes. Yes. And
Right.
that the thing that you mentioned is constantly used by designers, photographers, and anyone working with images. It's something
Mhm.
called pixel per inch. Is actually the resolution of the image. So
Right.
how much of our man-made measurement inches is these pixels supposed to cover, right? And all of
Right.
our digital or otherwise print di- images are measured with their resolution is measured with pixel per inches. So that if that analogy or if that idea is ingrained with us, I want you to stop thinking of images in terms of pixels. Think of images in terms of how much bright or how much dark that image is. Okay, so if we say the actual definition of a histogram is that it is a distribution of discrete intensity levels in a range 0 to L minus 1, and that means nothing to us because right now it is something that's just jargon. But again, going back to what I said just a moment back, if you think of images as regions of darker and brighter patches, what you will essentially note is that there are specific regions of the image where there's a really bright region and then there's a darker region. So if we try to plot the brighter and darker regions in this image, and first of all, we actually need to limit them. So if we just say that 0 is our lowest brightness or the most dark region of the image, which is probably this region or this region, we will say that this region, which is completely white, is probably the brightest. And we can just say that that's 100 or that's 10, right? So if we try to plot this image in terms of its intensity, in terms of how bright or how dark that this image is overall, we will actually end up with a curve that looks like this. We will probably note that maybe there's a little bit of gray area here, too dark area over here, and then when we go down, stuff like that, right? What this allows us to do is to view our images in terms of intensity and not their resolution or their sizes. Why is that important? Because we need to understand that our images do actually have regions where they are too bright or too dark, or maybe those brighter or darker regions reveal some really important information. Like, for example, you go for an MRI and you have an actual tumor. Touch wood, you don't, but you do have an actual tumor. And if there's a really brighter region and that's not something that you can make out or that you can plot in a graph, then it is not possible for the medical personnel who is looking at that image to decipher that, okay, this is unnaturally bright, or this region shouldn't be this bright. So this is probably an anomaly. So there are specific instances of image processing, or uses of images, where you do need to measure the distribution of intensity across an image,
So
right?
Ritvik, just asking a little question, like small question here, as I
Yes.
am not as well versed in these things as you are, because you are a resident photographer. Anyway, so the histogram here, so we are basically uh, measuring each intensity here
Mhm.
with the range capped as the least the least bright and the most bright, right? That's how we are just like we are.
Yes, yes. And so what you're essentially measuring is, there are two limits: the the most darkest region and the lightest region, right? And what you're measuring is how far along, like, how, what is the level of brightness of the, so when we are saying the histogram is about like this high, what we are saying is, what is the level of brightness, or what is the level of darkness, as you use them, for this region of the image, right? With respect to its darkest region and its brightest region. Does that make sense?
Perfect. Perfect.
And to
Totally
our
does.
audience, if is this analogy useful? Are we getting what histogram is supposed to be, and what it represents?
I'll be looking at the chat for answers.
Right. And like, if you do need, if you do find a question or a query, please do let me know. So
Yeah.
I'll pause and I'll bring that up.
Right.
So we just learned about histograms, how they are plotted, why they are required, and how we are going to cap them throughout the image. Now what we are going to do is look at something called histogram equalization, and
So, Ritvik, there is a question. I'm sorry to interrupt.
right.
This question is from Jim. He says, do we just change the dimensions for full color histograms?
Uh,
So I think what he means by the question is about
yeah.
the
So
histograms for color
for
images.
color images, so if we have colored images, we are not just actually worried about the darkest or brightest region. What we are
Mhm.
worried about is how the histogram is plotted across channels. And when I mean channel, what I mean by channels is red, green, and blue. Those are the three sort of lenses that allow us to view colors in images. And what we want in a colored histogram is to understand how much of red is this region, how much of blue is this region, and we do not do them separately. What makes that interesting, and like, this is out of the scope of this particular tutorial, but since this was a really interesting question, what that allows us to do is allow us to look at the entire image, and what we are essentially measuring is, what is the combination of red, green, and blue at this particular region of the image, and how high is one particular color. So you will find a histogram which is colored, and you will actually find what is the level of each color across each level of the image. And if you like, if you go to YouTube and search up photographers, or photographers plus histogram, or digital photography plus histogram, you'll actually see that what photographers do is shoot an image, and then through their camera, we are blessed that we do have these technologies with us. Through their camera, they are able to see which area is overexposed or which area is underexposed, and which area does have a warmer tint, which means more reddish colors, or a bluish tint, or which means blue. Basically, the blue channel is dominating that area. So that is how colored histograms are useful for images, and how we actually make use of colored histograms. So does that make sense? Is that clear?
Let's ask Jim that. Jim, is that clear? because
I think
that was a great analogy, Ritvik,
I
and
think
a great explanation too.
I do see a yes from Jim. Uh,
Cool. So I think
So
that makes
I'll
sense.
just move.
Let's
Yeah,
move on.
I'll move forward with the session.
Ah,
So
he said yes again, so it definitely made sense to him.
right. So before we move forward, notice that this histogram is not a straight line, right? It should not be a straight line. If there are levels of intensity that is being plotted for a particular image, it should not be a straight line. It should have peaks and valleys. So if you noticed that there are a number of peaks and valleys, it means that there are particular levels where it is peaking or dipping down, right? And what we essentially want to do with histogram equalization is to flatten that, is to make it normalized. And think now I want, so we went from left to right. We understood what this image means, where the intensities are and how that is mapped to histograms on the screen. But now what I want you to do is go from right to left, and I'll be actually asking these questions to the audience and to my friends here. So what happens if we make this a straight line? Anyone wants to volunteer? Dave, I think you're speaking on mute.
No. It's because I'm going to answer the last. I'm going to answer after Orithro because I am actually someone who is not that well versed with these kind of functionalities of OpenCV and image processing. So I'm going to go last.
Right. So,
Cool.
Archana.
Cool. So what I think is with your explanations, what I am thinking of histograms is that it basically plots out the intensities with respect to everything. Now, if there is a flat line, every intensity is the same with respect to the other. So I don't think it's going to have like very contrasting dark and bright patches. It's going to be a very standardized kind of an image, if that
Exactly.
if that makes sense.
Exactly.
Yeah.
So, as Arthur said, that is just spot on. If you make this a straight line, it won't have peaks and valleys. It won't have a region of the image that is extremely dark with respect to the other regions, and a region of an image that is extremely white with respect to other regions. It will just be a kind of a mundane image with something of a normalized intensity. And what is really tough to think about this, to think, is it won't be it won't be normalizing the colors. So what I mean by that is, when we say normalizing, or when we say that this is going to be a flat line, what we essentially think that there's a white region and this is a dark region, and we are going to normalize them. So this will essentially all be a gray region. That won't happen. We won't be making this a straight line and making our image a gray block. That is not what is going to happen. And that is the tricky part. The tricky part is not to think of this as in terms of colors. So if we actually normalize the colors, this would have been just a gray image, right? And if we actually normalized a color image, it would have been either a white image or a black image, depending on where the colors ranged. But what we are normalizing is the intensities. So it will have a flattened, more sort of a grayish look throughout the image. It won't have extremely dark or extremely bright regions. And mathematically, what that means is that we are attempting to apply a linear trend to our cumulative distribution function. And that is just a term, that is the probability of the intensities throughout the image. And if you do want to read up more on this, you will find links to Wikipedia, or we will be providing them. But at Pioneer Search here, we always want you to get started with code first. Code your way through the problem, understand it well, and then come back and learn the math, because that is even more effective. if you do want to learn the math, or if you do really need to understand the math before, no harm in that. But we do really recommend that you go through code first. And before we go to the code, this is actually what the results will look like. So notice that the image's contrast has improved significantly, but that has happened at the expense of boosting the noise in the image. And the reason why noise is present in the image is because there are regions of the image, like this is a nice image, probably from the Windows 7 wallpaper, and what is happening is there are regions of the image that are too dark, or that are inclined towards the darker side. And when the algorithm, or when our function or our code actually experiences or actually finds regions that are brighter, it is not being able to boost that. It is not being able to boost the intensities of that region with respect to the entire image. So what is happening is when so imagine this: you're at an interview, or you are at a viva, and the teacher asks you a question, or like the interviewer asks you a question, and it is not in your knowledge repository. What do? Either you don't answer it, you fail, or you make stuff up. And that is what the image is doing, like the algorithm is doing. It is not being able to boost the intensities of the brighter region, so it is making stuff up and throwing in noises. That is the analogy that you will find most effective for why noise is present when we are trying to boost intensities in an image.
You either don't say and fail, and
Make
or
stuff
you
up.
make stuff up and then fail again.
And by the way, we don't want you to make stuff up,
Exactly.
and we really do want you to succeed. So this raises an important question: that is it possible to improve the contrast or improve the entire look of the image without boosting the noise at the same time? And the answer is yes. We need to apply something called histogram equalization, and then make it adaptive. So the algorithm that we will be using is called contrast limited histogram equalization. But with adaptive histogram equalization, what we essentially do is divide the input image into m cross n grid, and then we apply equalization to each cell in the grid, resulting in a higher quality of the image. So if that did not immediately make sense, just hold on, because we'll be going through the code next, and that will make a lot more sense in a minute. So I'll just stop sharing the screen, and Auditro, do we have any questions, comments, anything?
No, I don't have any comments right now, but I would eventually want to discuss something with you and Dev.
Right?
I really liked what you said about us at PyMedSearch wanting people to code our ways through, like not get bulked up with all the math, all the theory, but do the stuff first and then get back to the math. So it's not that we don't provide the math. It is very important. It is equally important, but you need to have a baseball and a baseball bat and hit a few of them before you understand the theory of how the stance should be. You can't just practice on the theory and hit a home run. So that's something.
Also, the analogy that you use, it's kind of you essentially just described machine learning, right?
Right.
Repeating.
Right.
So yeah,
Yeah.
coming back to our approach, uh, thing is, I had problems earlier when I used to read research papers, and what I found most helpful was going through the code, because code language was something that I understood. Like I understood that when I assign a variable, or when I'm assigning a function, that like I know what the function is because I can see it in my with my own eyes getting defined in the code itself. So I can trace that back to its theory. That's why we kind of say go through the code, and that's how you're going to find a way back to the theory itself.
Absolutely.
Right, absolutely. And just to top it off, this is also advocated by Jeremy Howard of FastAI. If you guys know him, I think everyone knows in the deep learning space. So he says that it's always a hands-on thing first. Deep learning is not theory; it's more of an engineering practice that you experiment, you code, you fail, you code again, you fail, and then you succeed. And then you go back to your lab, scribble a few of the equations, think about the equations, and then you go back to code again. So that to and fro movement is very required, but you start out with your hands on.
Yeah, so that basically what Orithro is essentially subtly saying is you code and math will no longer be scary for you. Trust me, it's for experience.
Yes, yes. So with that, let's go into the code. And
Right.
is this visible, or should I zoom in a little bit?
I think zooming in a little bit might make sense.
Yeah, for
Yeah,
our viewers,
absolutely.
yeah,
Yes, it's
that's perfect.
visible. Yes.
That's good.
So again, as we mentioned, this is something that you will be having access to. You will be provided with these collab notebooks, and we really do advocate you to go home, or like probably you are at your home, so
At
stay at
home.
home and try out these collab notebooks, because they have been made for you, and they have been made with the intent for you to go through the code and understand it step by step and play around if you want to, right? So we'll be going through the
Absolutely.
code step by step and explaining everything that is happening. But if you ever feel like that this is not making sense right off the bat, or you need to cover a few more topics or a few more things in the academy,
Mhm.
we completely understand that and we want you to do that. But just bear in mind that taking in this information passively, even just sitting back and relaxing and enjoying this session, will be worth its while when you go back and watch this session later on, say 2 weeks from now, when we
Hmm.
you have covered the theory and the code needed to do that. So with that, what we are first going to do is download our code zip file, which has our images that we are going to experiment on. So that's downloaded, and then we are importing our essential packages for this: matplotlib for plotting, argparse for parsing the arguments. And we at PyMesearch work with code essentially with arguments. You will have codes, or code zips or collab notebooks that use this. But so it's a good practice to know it and use it as you need. And also CV2, which is basically OpenCV, that you absolutely do need for your computer vision journey.
So
And
if you guys are unfamiliar with what Python packages are, just again, I had used this in my lecture once. So these packages are kind of your allies, and these allies will help you basically get to the end goal of your coding, like whole coding journey, like in this
yes,
particular project.
yes. And so I don't know how many of you are familiar with Colab and or OpenCV for that matter, but as they've said, allies, all packages are allies that will help you. Turns out some allies do not get well with other allies, and Collab and OpenCV are two of them. They do not work well with each other. So what we need right now is a way to show or display OpenCV images inside Collab, and this is a custom function that we have built just to show it, right? It's not worth much, but it will allow you to display your images and check that whatever you're doing is correct or not. So it's just a simple function. It converts the image frame from blue, green, red. That is the order of your channels: blue, green, red, to red, green, and blue. And that it then it displays that with the title and the grid. So if you want the grid to be true, like if you want your images to have grids and know what is the dimension of your image, you just have to turn this to true, and you're basically set. And then it shows it. And all of this is done using matplotlib, and the conversion of color is done using OpenCV. So we'll run that, keep it ready, and then we are going to implement histogram equalization with normal, the standard histogram equalization without the adaptive nature of it. So if you remember, that was a straight line that you drew from the peaks and
Yep.
valleys. So this is
Mm-hmm.
what we are essentially going to do now. And for that, the arguments that we need is a simple dictionary. We need the whatever we are passing, the name of what we are passing, that is the image, and we need the path of the image. And we are just taking a picture of a dog. So that's done. And now we are going to apply the histogram equalization. So first of all, we are going to read the image through
Mm-hmm.
cv2.imdate and then convert it to gray, because we are doing histogram equalization for grayscale. And then we are going to perform histogram equalization with equalize hist. So equalize hist, a very original name, is going to allow you to equalize the histogram of your image. And so what you basically need to do is just pass in the image, and then you will have the histogram equalized image for that in the output. Do keep in mind
Right.
that this means that the image that you will have is uh, is going to is going to have a standard histogram throughout the image. It won't
Mm-hmm.
have higher peaks and valleys, and it won't be adaptive to the particular needs of the particular regions of the image.
Right.
So enough talk.
Show me the code.
Show me the code. Do you know who said that?
No, I don't.
Linus Torvald is it.
Should have guessed. Should have guessed.
So this is the image, right? This is the input image. It's of a
Mm-hmm.
dog, as we guessed earlier, and this is the histogram equalized image. And we can see that there are regions behind the dog, like occlusions or something is present,
Mm-hmm.
and it is not, you know, not perfectly clear or visible in the image. In fact, if you look at the entire image, not much has improved. I mean, there are regions that are a little bit darker, but the entire image is kind of flat. It has a standard intensity level. It is not that clear what details it has brought out, right? And now what we are going to do is implement adaptive histogram equalization with OpenCV. And the name of the algorithm that we are using is called contrast limiting adaptive histogram equalization. We do have a tutorial for this, and we also do encourage you to read up on the actual method if you are really interested. But if you do want to get hands down, as also mentioned, start with the code. Start with what it is doing for you, how well it is doing it, and then go back to the theory. And these are the arguments that we will be passing in. So what we need is obviously then the image path, and then we need something called a clip. That's our variable. So what clip is basically a limiting factor for your contrast. So you are boosting the contrast or bringing it down at specific regions of the image through this algorithm or any histogram equalization algorithm. And if you boost it way too hard, it will a, a place will just have a region will just have black spots, and that's not something that you want as anyone. You do not want an image to be completely darkened at some region randomly, right? You want that to be controlled by you. So that factor, clip 2.0, clip equals 2.0, is that factor which controls that contrast limit, right? And so think of it like a threshold beyond which the contrast cannot be boosted. And then what is tile? Tile is basically the 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 dimension or the m cross n block in which you will be breaking the image. So if you look at this image, and as I said, there is something over here which is not exactly visible in the standard histogram equalization. So what we need to do is tell the algorithm that this block is essentially separate from this block and from this block. So we'll be dividing the entire images to blocks, and then those blocks will have histogram equalization applied to them. So this block will not be affected by what is the entire histogram of this image. It won't be affected by how much dark the nose of the dog is, right? And that is
Right.
essentially important to us because we are making it adaptive. We are telling it, no, there are very specific regions in the image, and those regions have its very specific needs, and you're going to
Mm.
focus your attention on those needs. You will
it,
not go crazy.
it kind of is sounds like the when we are creating environments, each environment has its own needs.
Yeah, yeah, it does. So that's basically our arguments, and we'll run that. Keep it ready. And then the same steps as before, we are reading the image and then we are converting into grayscale because we are basically doing histogram equalization for grayscale. And then we use this create Clahi function. Clahi is nothing but the name of the algorithm, contrast limiting adaptive histogram equalization. And we are passing in the clip variable. We're passing in the tiles or the blocks that we need to pull out, and then we are doing something called clahi called apply, which is basically passing these functions inside this object or inside this variable, and then calling the apply function, right? So what it is doing is applying these functions, create apply functions to the image, which is the grayscale image. So let's go ahead and run that. We can see that it has finished running, and let's show it. And the details on the second image are like,
Significance.
yes, significantly higher. Nobody knew that these details were present. The dog didn't know about it, but like it's present. And think about how considerate the algorithm is to the background regions. Just by breaking the entire image into subsets, into smaller blocks, and then focusing the histogram equalization to those blocks only, not to the entire image.
Mm.
And that basically brings us to the end of this code walkthrough. So does this, like, did this make sense? Even if you are not absolutely familiar with OpenCV, did it, did you take something from it? How, I'm looking at the chat, people. So, and I would actually ask Auditro to do that.
Yeah, I would. I will. I am looking at
You-
the chat. Yeah, go ahead there.
so just a tidbit of like a trivia some kind, because since Ritvik is a photographer and he's a very good photographer at that, he told me once that this Clahe algorithm, it's still in use in some cameras, in some DSLR cameras. They still use it for the contrast boost. So it's very amazing to think that we are in 2022 where machine learning is slowly
Mm.
taking over the world, not in a Terminator sense, but it is. Everything uses, like, okay, most tasks uses some kind of machine learning in it, and yet there are
Right.
some classical algorithms, hard coded classical mathematical algorithms which are still keeping up with those machine learning algorithms, and that is, to me, it's a really amazing feat. Like, as we can see, the Clay is
Absolutely.
no joke. The output is so cool. Like, as Ritik said, the dog didn't know about the details that appeared on its face. So yeah, that's something I wanted to just put it out there.
And
That's
to,
really.
like, as I stop sharing the screen and like go back to my presentation, I would
Mm-hmm.
like to take something from Dev here and actually talk about it. Is that, yes, some DSLRs still use this Plahi algorithm, and the reason why it uses they use it is not because like they are classical algorithms and mathematical and easy to. Uh, so I am looking at a question
Yeah, I
about,
was going to interrupt you. So the question is,
yes.
Anjana, if I'm sorry if I'm pronouncing your name incorrectly, says I'm using Ubuntu version 18.04. I haven't installed OpenCV yet to follow the OpenCV and deep learning course. What is recommended? OpenCV via pip or OpenCV from source? If you could
Yes.
relate to that.
So we do actually recommend you to install pip install OpenCV contrib, which will allow you to have the contrib modules and access them. But we do recommend pip installable because it saves you the hassle of going through the source files and building them yourself. And we have, I think we do have a tutorial for installation of OpenCV on Ubuntu. In fact, the code
Both
snippets
of them.
yes, we the code snippets we showed a while back for installation of like for creating virtual environment is from that tutorial. And
Mhm.
Anjana, I want you to keep an eye on this live stream when it's over. So 1 hour from, or like even half an hour from when it's over, as YouTube processes it, we will be posting the links and the tutorials in the description box, and you will be able to access them as you go through them, right? And I do hope that you solve it really quickly.
Yeah, so Ritik, you were talking about how why Clahe is used in DSLRs. And
Right. And so basically what we want what I was saying was that there are, like, think of it like this: a
Mhm.
DSLR is something where the image is coming from the real world, it is coming into a digital form, it is going through the lenses, and then it is converging on a sensor, right?
Okay. Mhm.
And that sensor is giving you your pixels, your images, your colors. Basically, if you are seeing our faces, that is because of a sensor, right? Think of it like this: what are sensors made of? They're made of very, they're made of p and n type semiconductors, but they are arranged in tiles. The Clahe algorithm and the sensors come in and fit together beautifully, not by design. Some scientist somewhere saw this and was amazed by it and said, these two fit together perfectly, we should, leverage that. And that feels like a cheat, that feels like something that we would do, something that a school kid would do. But that is essentially what scientists do as well. They look at things that have no reason to go together, and by sheer luck and confluence they do, and that revolutionizes the world. So that is what we want to, like, we at PyMessage read papers weekly, regularly, and that is over and over what we see. You are, even if you are a beginner right now, you can be the like researcher, scientist, or contributing industry through that. It's not something that is way out of someone's league. So with
Right.
that, I'll
so
go
what
back
I
to that.
understood from this was you meant to say Clahe and the sensors, the PN type semiconductors in the DSLRs, they're actually soulmates.
Turns out, right. So, and if you are here right now, like, after these two sessions, I want you to stop and realize that you have covered a lot. You have
Yep.
covered how to create a virtual environment. You have covered you have learned about images, image histograms, equalizing those histograms, and you have also learned the code behind that. So that is a lot for day one, and that is a lot for 1 hour. So if you have done that, just take a step back and give yourself a pat on your back. And we do not stop here, and we do not want you to stop here. Number one, because we are on a flow, and number two, because we have that surprise plan for you. So the next part where we go, that we are going to go to, is called squeeze excitation networks. It is a form of deep neural network, which makes Orithro very happy, I guess. And
Yes, it does.
it is not, so we'll talk about this a little bit later on, but it is not the traditional form of neural network. It is a little bit different. And so I'll just give a brief introduction about it. In 2017, Hu et al., that's the name of the author, released the paper titled Squeeze and Excitation Network. And that approach was based on the notion that somehow focusing on the channel-wise feature representation and the spatial features will yield better results, right? And if that didn't make any sense, I want you to think back a while ago about what we spoke. We were talking about image intensities, and I just told you that do not think in terms of color, but in terms of intensities, right? So here,
Mm-hmm.
what we are doing is thinking in terms of colors. What we are essentially doing is what is an image? We all know, and we are probably tired of hearing that an image is an m cross n array, but it is so much more. It is not just an m cross n array. It has pixels in it. It has specific channels, the red, green, and blue, that create the illusion of colors. And what we have been doing in deep learning for a while now is taking the pixels, taking the value of those pixels and putting them inside a deep neural network and telling that deep neural network to perform certain tasks. And you know, as we stack on them, as we make the deep neural networks more and more complex, we see that it performs those tasks really well.
Mm-hmm.
But but for a second, what that does and what we now are going to do is not focus on the actual dimensions or the m cross n features, but focus on the channels, the red, green, and blue that make up the colors. And we will see how that will allow us to hunt for better features and achieve the deep learning task better. So
Absolutely.
this this is the idea. This is the architecture that was introduced by them. And what it does is assigns a weighted value to channel-wise features. So
Ritik, before
this,
that, can I take over just a little second?
yeah, yeah, sure.
So just to put everything in perspective, um, squeeze and excitation nets come much later than convolutional nets. So somebody who does not understand convolutional nets don't have to get overwhelmed because we are teaching or we are just discussing in a very casual manner about squeeze and excitation nets. But just to remind you what convolutional networks do is that they input an image. The convolutional kernels or filters, as we call it, convolve over the entire image in a spatial manner. What do we mean by spatial manner? In the height and width. It goes from left to right and then goes down, again left to right and then goes down and covers the entire image. And this representation or the kernel represents this particular pixel in a different manner, this particular pixel in a different manner, and so on. And as we stack a lot of convolutions over the entire convolutional network, what happens is we get some feature representations that are richer, in a sense that it takes or extracts a richer implementation or representation from the input image. And with that feature representations, what Ritvik was saying is that we often see that the kernels somehow in the initial stage of the kernels, it kind of understands what a line is, and later it understands what a human face is. So on top of lines, circles, it just kind of goes on to understand what a human face is, what a dog is, what a dog face is, what human legs are, what wheels are, maybe. And it eventually helps us into understanding about image classification or maybe any visual recognition tasks. So now that we kind of understood what convolutions are or convolutional neural networks are, we will now move into uh, what do you call it? The squeeze and excitation net. And before that, I would also want Dave to, just discuss with me. Does that make sense? What do you have in mind?
Yeah, so squeeze and excitation nets are actually a very a topic that I like a lot, because intuitively, to our viewers,
Mm-hmm.
I want to ask this. You are looking at the screen right now, you're looking at a video right now, you can see three faces in the screen. You are, by definition, intuitively you're registering our three faces, like our outlines, our hair, our glasses, or Anisha, you are registering the spatial information that is being shown to you. Spatial as in the height and width wise information. So
Yes.
when I'm feeding an image to a convolutional neural network, we are feeding it in this format itself. So it also intuitively kind of learns the spatial, like height and widthwise information better, as in like you tell us, like you are looking at us, you're looking at our face, and that's how you're determining, okay, there's a face in it. So obviously it might tell us that CNNs kind of work on spatial features a bit more, and that was the essence of squeeze and excitation network, to kind of deviate from that path and give the CNN an additional set of features to work on. So that is why this topic seems very interesting to me. So I'll let Ritik continue, and over to you, Ritik.
Yes, and yeah, before like as I do that, so also can you please keep an eye on the chat, see if anyone poses any question, and guys,
Absolutely, I'm doing that.
please do start putting in your questions if you need. And hope my screen is visible. Yes. So this is the architecture that was proposed by them, as and I was saying that it assigns a weighted value to channel-wise features, essentially modeling the interdependencies between the channels. So as Arthur was saying, and what I took from that is this this is, this is a like a normal block of image. This is an image, and then we apply convolutions to it, and then we get this second set of image. And if we keep on stacking those convolutions, if we keep on doing that, we will essentially build features, understand representations, and probably have them recognize a license plate. But what does modeling interdependencies between channels mean? So Dave or Throw, anyone wants to pick up on that?
uh, do you want me to share the screen?
Yeah, sure. Go ahead.
Okay, give me a moment. Okay, I'm having a little issue. Give me a little moment.
Take your time if you want us to share.
Okay, can you see the image? Sorry, can you see the image here? Is it
Yes.
visible?
Yes, 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 it is.
Yeah. So when we are talking about this block, this is a block of Ritik called it an image block, and it can be an image block. So how do
Mhm.
question becomes, how are you going to view this image or this little block, this yellow block? I want you to kind of remember this yellow block. This yellow block is called X, and its height is h dash, width is w dash, and the channel is c dash. So if I have to just make it even more simpler, I will ask you to imagine this little yellow block as this. Yeah, no, this is not a joke, by the way. I want you to imagine that yellow block as a loaf of bread, where each slice of bread represents a channel. So when you stack lots of bread one by one and then combine it together, that is this one yellow block. So that is how I want you to imagine, if if you are new to CNNs and if you are new to feature maps. So I want you to imagine that yellow block as a stack of breads. So then we are applying some transformation that is called FTR, or F transformation, or you can just think of this as a convolutional layer. So if this initial X yellow block is an image, it's an input image, an red green blue image, then think of it as three slices of bread stacked together. That is all that is. That's the simplest way I can probably explain this. So now that this is being passed through a convolution layer, we are going to get a different feature map. We call it feature map U. Now this is different from X because X has now been passed through a convolution layer, and we have gotten the output as U, which has
Mhm.
different height H, width W, and channel C. So Aritra, do you
If
want to
my
take over?
yeah,
Sorry.
no, 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 it's not. It's absolutely fine. It might just be easier visually to shorten the second feature map or U for our viewers, because it's not the same. Yeah, exactly. Shorten or maybe elongate it, because that drives the point home. After X goes into FTR or function transformation, it has to be dimensionally different or maybe channel wise different than the one that went in. So the output must always be different, or let's not say must, because there are a lot of convolutions that don't transform dimensionally but will transform the pixels or the values in the box, or the breads, as Devjyoti said, loaf of breads, the breads will change. From white bread it might go to brown bread, but it will change. So that is something which I have to drive. Yeah. So
Yeah. So basically, what Oritra is saying, you might start with 6 slices of bread. Now, once it goes through a convolution layer, you might have 12 slices of bread, but each of but different size than what was it when it was slices of bread. Am I right, Oritra?
absolutely. So that is a really good analogy. I didn't think of it as breads, but yeah, man just whipped out a loaf of bread and made squeeze and excitation exciting. So yeah, Ritvik,
Yeah.
let's go ahead.
Yes. So
So should I
that
stop
means,
sharing, Ritik?
yeah, I think it's no longer visible.
Oh, sorry.
Good. So I'll just go over, start sharing again. Give me a second. And as we were saying, this is the architecture that we were talking about. So again, if this like we have been like showing you this architecture for a while now, and probably it
Mm-hmm.
does not make a lot of sense, because yes, we do understand channels, we do understand how features are, how convolutional layers are stacked on top of each other, and then we extract good features from them. But what is this jargon? Like, what does this mean? And you don't have to worry, because we actually have cropped out all of these into separate stages, and we will be making it our mission to make this easier to understand. And even after that, if you feel like you need to take a step back and go through the fundamentals of deep learning, please do that and then come back. Please don't think take this and put it in your watch list with 1,000 other videos. This is something that will help you to connect the dots later on. So as we were saying, first we have an input of X, and I'm going to go through this because like Arthra has already done that. That has dimensions H dash, W dash, and C dash. And X is passed through a transformation, that is the convolutional operation. And next we have a feature map, that is U. And that has dimensions H, W, C. And if we go on repeating this again and again, we will have good features. But that's not what we are doing today. What we are going to do is take this, and as they've said, you have a loaf of bread, your channels are your loaf of bread, and you squeeze them, right? So think of the image as a squiggly jelly box right now that you can press and stretch as to your heart's content. So this box, yellow, the U, is actually squeezed to a box that looks like this. And what do these mean? 1 plus 1 plus C. So if you notice that we have a C here and we have H and W here, so does that mean that H and W become 1? Yes, they do. What we do is squeeze it hard enough so that our height and width becomes unit, and then we have only our channels. So does that make sense?
Yeah, it does. I'm also looking at the chat so that we understand how people are taking it in, because it's a highly advanced topic. It's and it's also a new blog post that
Right.
Devjyoti has authored for PyMed Search. So
This
we
Monday.
just, yeah, this Monday. So it's fresh off the PyMed Search
Oven.
bakery. Yeah.
Yes.
And come to think of it, I also think we need to trademark our analogies, Ritvik. What do you think? Like the loaf of bread, jelly box, on point, on point.
Yeah, so squishing your loaf of bread or your images as squeezing them is something that we call in deep learning terminology global representation of channels. We really hope that they were called squishing or jelly squashing, but they are not. You like, so it is something called global pooling that happens, and then you get your height and width as unit one, and then your number of channels preserved as it is. So we have that. Now for the next part, where we will apply the excite operation. So what we are going to do is create a small dense network. So if you have some prior experience with deep learning, you will know what a dense network is. If you do not worry, because these will all start to make sense as you go through all the fundamentals of deep learning in Deep Learning Academy. So a dense network is basically your convolutional operations with your non-linearity is pressed between them, and the non like we are going to use a Sigmoid activation function for this dense network, and that basically ensures that we are not using a simple one hot encoding of this representation. And so therefore, why is it why is it really important that we do not use one hot encoding?
Okay, so then I guess we have to take a little step back and understand what one hot encoding means. So
Yes.
okay, so let's assume we have three labels: the Ritvik, Orithro, and Devjyoti. So when I'm talking about one hot encoding, I will when I and say okay, let's bring label Ritvik ahead. So that would be in the place of Ritvik's face in the stream. Think of it as one. In place of Orithro, think of it as zero. In place of Devjyoti, think of it as zero. So the representation of Ritvik becomes 100. Now, when I'm talking about Orithro, think of Ritvik in place of Ritvik face, we have zero. In place of Orithro's face, we have one. In place of my face, we have zero. So Orithro representation becomes 0, 1, 0. Again, when it comes to me, then if you follow the trend, it will become 0, 0, 1. So when I'm talking about one hot encoding, I just want the bit of one particular label to be turned on while turning off the bits of all other label. Hence,
Kind of
Ritvik.
like a switch.
Exactly. But but in our task today, we want to understand how all the channels, what kind of effect all the channels have. So if we just
Hmm.
apply one hot encoding here, that would mean we would only focus on one channel, and that's not what we want. We want
Hmm.
to understand how all the channels affect our overall loss function or overall feature representation. So that is why
Right.
we do not want to take the approach of one hot encoding. So if
Right.
Orithro and Ritik want to add, you guys want to add on to that, that would be great.
So what I
Trademarking our analogy. Sorry, Ritvik. I'll just
go
go
ahead,
ahead
go
with
ahead.
with the analogy. So we don't want to take away a bread from the loaf. We want to give weightage to each and every bread of the loaf, right? So yeah,
And
Ritvik, you were saying.
what I take away from that, um, like nowadays speaking in terms of computer vision or deep learning, is we are not saying that think of these colors as discrete values. Think of blue, red, and green as discrete values, but as a continuous spectrum. Because when we are viewing the image, we are essentially viewing a continuous spectrum, or we are seeing the illusion of it, and we would want the deep learning network or the network that is going to be modeling this to have that continuous spectrum modeled through it. It should not think of it as discrete values, which, like if we used 0, 0, 1 for red and 101, sorry, 100 for blue, and so on and so forth, it probably would have given us a discrete value of zeros and ones, a representation of zero and ones for the image. Is that correct?
Yep, it does.
So we also do have an image, and this is from the actual paper itself, where we get an idea of the dense network from this figure. So, like Arthur, you want to uh, tell us what is happening here and
At the
how?
yeah. So the first thing about this picture is that it's very intimidating for anybody. It's not
Yes.
only about a beginner who goes through a paper and sees this image. It's also intimidating for me. But the first thing that I want to make sure is that inception, scale, X tilde, HWC, don't have to look at anything. What we did in our like our tutorial in pyramid search is that we just took the global average pooling, FC as in feed forward network, ReLU, FC, and Sigmoid. Those parts are the of main focus. So, Ritvik, could you like at least turn the cursor over the part which I'm talking about and not look at the inception and scale?
Yes, yes, I can.
So
Is
these
my
are the
cursor
parts.
visible?
Yeah,
Yes.
it is. So just the global, yeah, exactly what Ritvik is showing on his screen is the part that I want to focus all of you on, and not the scale and inception. Inception is a different module from Fair or Microsoft. I'm not sure, but we don't want to look at them because it's just an architecture. And another thing that we want to um, put out there is that squeeze excitation is a detachable module. What do I mean by detachable? It's a plug and play kind of a thing. So you have an architecture, say an AlexNet from 2012, or say a
Or a
ResNet from
simple
20,
deep learning network.
or maybe even a simple deep learning network, and you can just use as a Lego piece the squeeze excitation block and put it in, and it's just going to work out of the bat, and it will, and that's a guarantee from the papers, it will give you a little bit of an accuracy booster. And it's also a good generalizer as well, but we are not going to cover them in this session. But
Yes.
the main focus of this tutorial is that global average pooling, which I'll cover a little later. Global average pooling squeezes the entire feature extractor, like the loaf of bread was squeezed in. So that's your squeeze. FC ReLU and FC and Sigmoid are the excitation bit, which Ritvik is going to cover a little later. So you squeeze through global average pooling, and you then excite whatever you get through the FC, ReLU, FC, and Sigma. So those were my bits. Yeah.
And I also see that it is like there's a certain division of the channels by a certain
Hmm.
factor, and then we
Yeah.
regain the channels. So it is sort of like it goes through a pipe, and then that pipe gets constricted, and then
Hmm.
it releases that again.
And
So
in deep learning literature, it's called a bottleneck, as in the
makes
bottle
sense.
gets construed and then opens up. So the bottleneck, what a bottleneck usually does. Why do deep learning engineers or academic people in deep learning space love bottlenecks? Is that from a representation space, it constricts down to a different representation space, which is always smaller than the one which it came from, and it also gets enlarged or regained to a similar representation space. Now think about it. You have to have a proper squeeze, and then you have to regain it back to a proper set. So you can't have information loss in that bottleneck. And when you say that you can't have information loss, it means that even with low dimensions, like in the bottleneck, the dimensions are not that great, it has to hold proper information. Like with lower dimension, it's going to emulate an information from a higher dimension. So deep learning engineers love constricting and also enriching the representation, for a lack of a better term, enriching the or boosting the representation, and then again regaining back. So hence you find a C by R. So R means the value by which, or the ratio with which you can constrict your information. Am I making sense, Dev? You were the author for this blog post, so
Yeah,
it would
absolutely,
be great.
absolutely.
Yeah.
I was like, I couldn't have put it any better myself. So I just like to add two things. The first one, if this is still a bit confusing for you, go back to our analogies. So currently, our information is in the shape of 1 cross C. We can see in the image that it changes to 1 cross C by R. So when think of it in this, when the information is in this shape of 1 cross C, we are in the Milky Way galaxy. When it is in the 1 cross C by R, we are moving to another sphere. Let's say the Andromeda galaxy. We are just representing information that we have in in a different sphere where the dimensions may be a bit less, but we have to ensure that there is no information loss. Now the second question that one might ask is, what is R here? The thing is, R is a ratio that has been spoken about in the paper by the authors. Now this is tad bit advanced, like you will be needing to go through the papers for this. But what it essentially is they have thought they have like basically worked on several values of R, and they have said, okay, this might work better, this might work better, and so that's why they have just given us a general idea of what R should be or can be, depending on your needs.
Right. So I think we have covered the entire theory of. Am I audible?
Yep, you are.
So I think we have covered the entire theory of squeeze excitation network, and why is this thing that deep learning researchers and scientists have thought about, and they have like put up a paper on it. Now what we essentially need to do is go through the code and understand what
There's
the results
one
are.
thing though, like one thing to think. Could you just go back to the image, like picture of the architecture once? Yeah. So so the complete architecture. Yeah. So to our users, just mentioning it again, you can see that after the FEX or F excitation is done, there are different colors in like representing that each channel is a different color. One is yellow, ochre, blue, light blue, light green, and light purple. So these colors are essentially telling us, like these are essentially the weights that have been assigned to each channels. So the model has now worked its magic, and then it is telling us, okay, assign this much weight to this channel, this much weight to this channel, and then finally, in our final F scale shape, we just multiply those weightages with those channels, and now we have a complete feature map or complete loaf of bread where we know which loaf of which slice of bread is more important than the other. So yeah, Ritik, continue.
Yeah. So, and I just wanted to mention that we are almost done with this, and we'll just go through the code because we already know the theory about this. We'll go through the code, and then we have finally the surprise that we have planned for you. So, with that, I'll stop sharing and bring up the code.
So our viewers, do you do you guys feel that this is a tad bit too complicated, or are you enjoying it so far? Please do
Yeah,
not
that's a
shy.
good
But
question.
Yes, please
please do
let
not
us
shy
know.
away. Yeah.
And if
Right.
you ever think that we are going too fast, or this is something that is not making a lot of sense, please post in the chat so that we are aware of the of of any problems that you are facing, and we can solve it here now and interact with you.
A feedback
So,
signal for our deep learning more minds.
yes, and Auditro will keep an eye on the chat while
Yeah, I
I
will.
go through the collab notebook. Hope this is visible. Should I zoom in anymore?
Yes. No, it's absolutely fine.
So, usual practice, we download our code zip file and keep our dataset ready. So here are our packages, allies as they've calls them, that we will be using for this particular project. We essentially take the layers that we will be needing from TensorFlow.keras layers and the dataset, which is CIFAR 10, which is a dataset of 10 particular classes that we need to classify. That is the task for the dataset. And we also take in NumPy, we import TensorFlow. Don't worry if you don't understand why these specific imports or how these imports are happening, because again, those will all be covered in your deep learning, OpenCV and Deep Learning Academy as you go through it. So we'll import our packages, and that's done. Now here's the config file, which basically tells us the configuration of the model architecture that we will be using. And here's something that I wanted to understand right now. We we just mentioned, like, we have been talking about squeeze and excitation network for the past like 30 minutes, and we have just told that it does give good results. So what we are going to do is take a normal network, take a normal deep learning network, and take the squeeze excitation network and compare them side by side and understand what's so grand about it. Why are we putting it on a pedestal? So that's just something that you need to keep in mind. Normal deep learning network and the normal deep learning network with the squeeze excitation block, and we'll compare the results at the end. So we define the number of convolutional layer filters and dense layer units. So 64 and 4096. Input shape is the shape of the data set that we are using, or the images. So they're 32 cross 32 n cross n, and number of channels is 3, as we have been saying. Now we are using a kind of species of the VGG model. So it's like it's um, it's it's not exactly the VGG model. It's
Yeah,
something
it
that
is
they
not.
have made simplified. So Arthur, like, what was the reason behind the simplification?
The simplification. So as I said previously, squeeze and excitation is a network, which is, it's not a network, it's a module. Let's say it's a module or it's a Lego block that is pluggable, right? And I wanted readers to really focus on what squeeze and excitation does and not what it is part of. So it is eventually just a squeeze and excitation network, and not we are not focusing on VGGs, we are not focusing on rest nets, we are not focusing on inception nets or anything. So hence what I did is I tried building a VGG, a very minimal VGG network, which is not even going to give you CFAR accuracies of 75%, as you will know later. But the fact that squeeze and excitations can be so easily plugged into any architecture, so that was basically the whole point of giving or simplifying the entire thing.
So we
And
have a
David,
comment.
yeah,
Yeah,
so you can go ahead.
I think that is exactly the point, David. So you can, as Arthur said, use it as a Lego block, attach it wherever you need it, and have a performance boosting.
But yeah,
So
David has made a good point. It does add a bit of computation cost, because
Yeah.
now, since because of that additional Lego piece, there's a little bit of more computations to be done.
Hmm.
And but let's be honest, that's a trade-off we are willing to willing to undergo.
yeah,
Right.
so back to our VGG models. So we have the blocks that we will be using for our VGG models: 64, 128, and 256 blocks. The number of classes for the CIFAR 10 data set is 10, very original. And the ratio for the squeeze excitation is 16. This is the R that Jyoti was talking about a while back. The R that you bring
Bottleneck
it
R.
down by, yes, and then you regain that. Optimizer is Adam. It's a very standard optimizer. The loss is sparse categorical cross entropy, which is a loss function. And the metrics that we will be using to determine whether our model is doing good or not is accuracy. And we'll be training for 100 epochs and a batch size of 32. So those are our configs. Let's go ahead and initialize them. And next we move on to the dataset part of it.
Hmm.
So we standardize the dataset first. By standardize, we mean that we take the mean and standard deviation and then normalize the images through that, and then we return the standardized dataset back to the functions. We also have a model for fetching the CIFAR 10 dataset. So the cipher 10 data set is fetched with the load data function, thanks to TensorFlow and our allies. And we basically split them into a 90-10 half. So this is, so people new to deep learning, you will need to set aside a certain portion of your data for validation and for testing. So that is our split. 90% of our data is for training, that is 10% is for testing. So that is what we do here, and then we return the train and test and validation data sets respectively. So go ahead and initialize those functions. We'll call those functions. You can see that it's downloading the data set. And again, these the 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 purpose of making these into collab notebooks is is having you take them and play around with them as to your heart's content. Change the data set split, change the data set itself, change the network architecture, and see what happens. Change
Change
the
the
hyperparameter.
configurations.
Yes, change the parameters and see what happens. So we have finished fetching the network, and we'll go on to building the models actually. So we have a class called VGG, and inside that we'll first initialize the input shape, which is 32 plus 3, our image shape. Then we'll initialize the ratio, the blocks, the number of classes, uh, everything that we have defined in configuration a while back. We'll create a stem block. So the stem block has a conf2d layer with a kernel size of 3 plus 3, strides of 1, and an activation of ReLU. So, and then we'll return that, return the information passed through that, and then we'll create a learner block. So for the learner block, we'll group the blocks together and then return it, and then we'll create a function for grouping. So the function for grouping basically means that you iterate through the layers, and then you apply max pooling, and and then ReLU nonlinearity and return, right? And there is something called is squeeze and excite. So that is a flag that we are going to set. So remember, I talked about having two models. One is a VGG model, and the other is a VGG model with the squeeze excitation block. So
Right.
what this is going to do is check if that flag is set to true or 1. So if that is set to true, we are essentially telling, no, you take the second model and you attach the Lego block on top of it, and then you see how well the performance is happening. So this variable is actually that flag, which tells us if it is if we need to attach that Lego block or not. And basically we call another function called squeeze excite block, and apply a nonlinearity of ReLU and return it. So inside the squeeze excite block, what we do, and I want you to remember the architecture right now. So is it possible for Auditro to pull up the architecture along with
I'm
the
sorry.
screen? Just for
I'm sorry, I
once.
didn't. Yeah.
Can you pull up the architecture of the model?
The squeeze excitation, right?
Yes.
Yeah, I'll do that. So
We do want to be connected, or I can do it.
it would be great if you did it, because there is some
Okay.
problem with mine.
So just give me a second here.
While they kind of figure the technical issue out, I just want to reiterate the fact that when we had said about like the analogy of adding the Lego piece to the model, that is basically the what the Boolean flag was doing, and that is how simple it is. Like it is actually just an addition to your model. You're just like it's this is an arm. You're just putting a glove on it. That is how easy it is.
Yes, and the reason I pulled up the architecture once again was this. If you can see is my cursor visible? Right?
Yeah.
Yes, it is.
Yeah. So this is the part that we are going to be building now inside the squeeze excite function, and this part, the shortcut. So like this is kind of a shortcut that will allow you to go go to here directly. And this part of having the so the dense network is going to build the excitation. So that is what we are going to do right now. Before, of course, before squeezing it, like after squeezing it. So first we do the global average pooling and then squeeze it, and then we do the excitation, and we also build this. Right? Does that make sense, guys?
It does.
So with that, I'll share the
I'm also
collab
looking at the
notebook.
chat for answers from our viewers. Does that make
Yes.
sense to all of you? Because we have gone through the code, we have the PyMessage blog post author with us, so that would make sense to him. But for the viewers who are very new to this or maybe pro in this, how is everything coming up? That's our question. And Ritik, you can move on.
Right. I'll be moving on, and Arthur will be keeping an eye on the chat. So
I'll
do
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 that.
let us know of your answers. And so here's the squeeze excite block. We take in the input, and then we first calculate the number of filters the input has. Um, and then what we do is squeezing it. And for squeezing, what we use a global average pooling across the filters, which reduces the input to a 1D vector, 1 cross 1 cross C, if you remember. And then we reduce the number of filters, like as we were saying, a pipe and then a bottleneck. So we constricted by R our ratio, and that ratio is 16 here. We do that by passing in it through a dense, and scaling down the filters through the ratio, providing an activation function of ReLU. The rest of it, if it does not make sense right now, it will slowly, but just take this in as we go, and enjoy the ride. The next part is the exciting part. We have the sigmoid activation function, and then what we do is to pass that through the sigmoid activation, get the output, and then we multiply the shortcut. So if you remember, we had this kind of a hexagonal, like upper hexagonal thing, and this is that part where you pass it through the sigmoid, you have done the excitation, and then you multiply it with the shortcut, right?
So
And
this is
then
the
just
part. Yeah, sorry. This is the part where the different colors you could see in the diagram.
the
Is it?
weights the weights
Yeah.
are distributed for the channels, exactly. And then you return it. And if it feels too good to be true, it is, because this is all there is, right? There is nothing else for squeeze and excitation. And then we build the classifier, because we do need a task to evaluate performance. We have our dense layers, and then we provide them with activations, two ReLUs, and then a softmax, because we are actually doing classification. We need to understand the probabilities of each classes. We return the value, and then we actually build the model. So we take in the input, pass it through the stem block, through the learner blocks, the stem and the learner in the very beginning, and create an output, through the classifier, and then initialize the model, right? And then we train the model. So for training, we compile it with our optimizer, Adam optimizer, our loss function, categorical cross entropy, and then we provide the callbacks, and we provide the callbacks of our loss, and we tell it to stop if the loss plateaus at a certain region, and then we fit the model with model.fit, and that is basically what we need to finish training, right? And we will run this code. That is done. We will now actually initialize the VGG model and build it. So again, two models, one with VGG, simple deep learning network, another with VGG plus the Lego part of squeeze excitation. So first we'll build the simple VGG network. We'll have all of the things that we required, our number of blocks, number of classes, dense units. If it is squeeze excite, and you can see that we set that to false over here, then we pass in our optimizer, our loss, the metric that we are tracking, and then we build the model, right? And in the in the like we after we build the model, we also train it. We pass in the training data set and the validation data set and our epochs, 100 epochs, and the batch size, and then we evaluate the performance, right, of how the model is doing. So let's go ahead and run this. And while this
While
is
it
running,
runs,
so
yeah,
Dev,
good.
how do they actually learn the weights as they go through
Yeah.
training?
So, would you mind if I share my screen?
Yeah, sure. I mean, I'll let everyone know if when it's finishes training.
Okay, cool. Is my screen visible? Just confirm once.
It's not yet. I think it should be now.
Yeah,
Is
it
it?
is now.
Okay, okay, cool. So one thing that should be going in all of our viewers' minds is, how does the model know how to assign the right weight to each channel?
Hmm.
So, so the answer here is actually, in the global scale, it's actually simple, because what is the overall task of your model? Your overall task of your model is like, you're passing in in a CIFAR 10 data image, and your model is giving a label for that image. If the label is wrong, then some gradients get back. It might sound a bit complicated for it, but essentially what it is, that if the wrong label is predicted, some recorrection is going to be applied throughout the model. So let us assume that first iteration, some random weights has been assigned to each channel, and the model has predicted the wrong label for an image. Now that means the this wrong label will now instruct the model to to rearrange the values inside it, and this rearrangement will also will be applicable to the weights that have been assigned to the channels. So that is how, like, sorry about that, the first time it's going to give some, like, assign some random weights. The slowly it will try to try to rearrange it so that it comes back to course, and at one point it's going to assign the channel weights in such a way that the predictions are going to be correct, and that's when the model will know, okay, so now I'm in the right path, let's keep going in it. So that is how it essentially assigns the weights. Was I clear, or you guys want to add anything more to it too?
Absolutely clear. Just a little analogy, as we are the team that provides a lot of analogies. Tuning of knobs. So when
Ah,
you have a speaker, if the music is too loud, you go down. If the music is too low, you go up, and you tune the knobs. So something which Dave correctly said is, when you have a mismatch of your predictions to the original labels, you tune the weights or you tune the knobs so that it goes closer, and if it overshoots, you again tune it so that it again comes closer. So something which we call convergence of a lost landscape, but it's a mouthful, we'll not go into that. But think about volume knobs, tuning, and what he said, and it's going to be fine, I think.
So I'll just
that's
share the screen again
perfect.
because it has finished training.
Oh, is it? It did. Wow, that's
It did.
quick.
It did. It ran for 10 epochs and gave us an accuracy of 74.12.
Mm-hmm.
And that's just something that we would probably want to note. 10 epochs and an accuracy of 74.12,
1, 2.
right? And then we built the VGG model with the squeeze excitation, and this is the exciting part. So, like,
Exciting part, no pun intended, Ritik.
yeah, yeah, and
Exciting part.
this is the exciting part because this will allow us to see if it actually improves or not. My bet is it does. So we
Everyone's
just,
bet is that.
yeah, and for this one, I'm not going to go through this again because I've actually explained what we are doing here in the previous part. The only difference is that we are passing is squeeze excite flag to be true, which means we are telling, this is the part where you attach the Lego model and you see if, squeeze excitation is improving your accuracy. So that is there, and now we train.
And Dev, just because we are uh, on training and it's going to take some time, do you think that the idea of squeeze excitation is very basic? Like it's very simple. What I think is it's very simple, but the execution is so top notch that it always kind of strikes me as that paper that you always need to read. Does that happen to you?
Yeah, like coming back to the first thing that I had said, even when we are looking at things, we are we are identifying them. Like in front of me is a computer screen. It's a rectangle, right? So I
Hmm.
am identifying it using its spatial height and width feature. Intuitively, that's the first thing that we also would see. Now they are like, that was ingenious to just veer off the path and think, okay, how about we give the model some additional features to choose from? Like we're just reinforcing it with some additional features. And
Right.
so when I first read the paper, it was devastatingly simple, and so simple that it made me think, I didn't think of that. Why did not I think of that? That's something that it made me feel like. So
So many
there's
times.
always, yeah, there's always papers like these, and these are really good papers, no matter how much you hate the authors for coming up with the concept before you. No, like nothing. Only love for the authors.
And do you have, due to the fact that you said that you read a lot of papers, do you have something for our readers to take away from this? Like, how do you approach a paper, or what excites you to read a paper? Because it's a, what do you call it? It's sometimes difficult to just enter into the world of research papers because it's mind-boggling. So, what do you have to say about that?
Yeah, it brings me to the mantra that I use for myself, is that no matter how hard, like how difficult of mathematics you see inside a paper, in the end those are just numbers, right? Those are just numbers, those are alphabets. You will, like, they do not come from something mystique. They
Right.
always they will come from some definite paradigm, not definite rule that has been said before. So
Hmm.
these things you can tell yourself to always make you grounded, so that no concept, overwhelms you. So that's one
Right.
thing that I keep in mind. And the second thing that is that, if a paper starts off as very scary, what I do is I go and check the results. And that gives me some additional motivation to get past the scary parts. So yeah, you can always do that. Both ways work. What about you,
That's
Aritra?
that's a good way of thinking about it. I never thought about um, what do you call it, the going through to the results just when it's very scary or very daunting, like let's just read this section because I know there is something waiting for me. It's similar to our session. There's a big surprise right at the end. We just need to hold on tight for like little epochs, and then we'll disclose the surprise. So what works for me is that I love doing Twitter, and there's a lot of hype, but you have to cut down through the lot of hype and read papers at a regular interval. It's kind of like a routine for me. It's not something um, which I have to do. It's something which just happens. And there are papers, there are implementations that don't work, there are papers that work brilliantly, but I don't have that amount of compute to, like, train larger models. But it's always easy when you have peers. Like I have Dave, I have Ritvik, whom we kind of talk every day on something which we read, right? And there comes in discussions, there comes in positive constructive feedback, and that helps. So I would recommend our readers to also form allies inside of the academy, so that you can go to a reading session all on your own. Maybe broadcast it, give us the links, we will just drop in and check how our students are doing. And yeah, that's basically it. And I also see that we have a significant increase in our
Yeah,
accuracy.
speaking of how people are doing, our model with the squeeze excitation has really done well. I think in 10 epochs, we have 75.98, whereas in 10 epochs,
Mm,
we had something
74.14.
74.14. That's a
Huge
significant
boost.
improvement.
Yeah,
Yes,
1%
and
increase in accuracy.
you have to remember that's 10 epochs of comparison for both of them on the simplest possible architecture I have seen for a model,
Yeah.
but this is what it gives us. And imagine having your own deep learning model doing your own task, taking this one little simple thing that you learned here today and just attaching it as something that is just plug and play and go moving forward. And that brings us to why our code has like so many functions and so many modules, where we could have
Mm,
just made them a little simpler and a little linear to read. But having like functions and having separated modules that you can take out and put it in another project really helps. And that's what we keep on doing. I think in some sense what Dev and Arthur were speaking about were talking about when they were talking about implementations, is that is also that scientists and engineers do all the time. They have ideas and they have things that they think are really good, and then they take across models from other pieces of literature or other places from the community and just plug it in and hope to God it works, and it does, and that revolutionizes the space. So if you even if this made very little sense to you right now because of where you are at your deep learning journey, we want you to take this little iota of thing back from this session, where you understand that yes, everything is possible. It isn't rocket science. It's just taking some models here and there and you know attaching them as Lego pieces. So with
even if
that
it
as
is rocket science, you will be able to understand rocket science if you read enough papers. So it's just a learning journey. So
yes,
just
and we'll
stick on
stop
to it.
sharing right now and bring you to your surprise. Just give me a second.
Oh, another way of simplifying your deep learning journey is always associating the concepts with some kind of an analogy that you will understand better. Like what I do is I always try to just put it in some way or the other, maybe some pop culture thing or just a loaf of bread, if you will. So yeah.
Yes, yes. Root it to something that you understand. Always do that. Do take something that you understand and make that your anchor, your reference point, and then root it into that. Root your newfound knowledge into that, and that always make more sense. So I think people have waited patiently enough. We have told them to stay tuned for the surprise, and we are finally at that stage where we are going to reveal that. And any guesses what that is? Keep, or keep an eye on the comments, see if anyone can. Yeah, not for
I,
you, I guess.
I am as I am as eager as everyone else viewers are because
Yeah, so this is the like big surprise, pot of gold at the end of the rainbow, if you will. So this we are offering a 30% off just for this session, just for it's a time limited offer. So just for this couple of hours till tomorrow, and we are doing that on our most comprehensive product yet. We are doing that on all of our books and courses that you will be able to avail for 30% off. We do not generally give out 30% off discounts, but since like this this audience has patiently waited with us and gone through this journey of creating rooms for your development pipeline, and then creating balancing out images with OpenCV and histogram equalization, and then actually going into deep learning, and then solving a deep learning novel architecture with us, and then seeing the performance enhance in real time. So this audience has been with us through that journey, and like it is no less of a feat. So what I would really appreciate if you do not stop here, and I by that what I mean is go ahead, take the resources, take the tutorials, and try them out on your own. And also, do not stop here with understanding of how far you can go. If that book or that course seems like something that is not possible right now, it will be. I promise you, it will be. Because the key is not understanding everything on day one. The key is doing it for 365 days and then seeing where you are. And that is where this comes in. If you scan the QR code that's on the screen right now, you will have 30% off on our most comprehensive product. We will also be putting the link to that is a QR code on our description, but we will be removing that particular link by tomorrow because it expires tomorrow. So you will no longer be able to avail it. We think that you know this is really worthwhile. This will be something that will let you go on a much higher journey on your deep learning and OpenCV practice, and that's it. If you enjoyed the session, we have left a couple of links in the chat. We have told you like to leave us testimonials. Please do that, or you can chat us about how if you have enjoyed it or not. Again, thank you for staying with us. Thank you for doing this, for choosing this for yourself, for staying with us in this journey where you have actually achieved uh, creating these three projects for yourself. Again, once more, I'm like putting this up on the screen. If you want to, you can take a picture of it and then just decide later on whether you want to, take it or not. Dave, I think you're speaking on mute.
I just wanted to say to our viewers, like, this is what you have achieved today. Like, sticking through all this, like, it really deserves a pat yourself on the back and tell yourself, good job today. Like, you made lots of strides, and that's a really great thing. So do not think this is all for nothing. Once you continue your deep learning journey, you'll understand the significance of little pushes like this. That's all I wanted to say.
Yes, exactly. And I'll keep this channel on for a couple of more seconds to see if anyone has to say anything in the chat. If anyone has any questions, any queries, anything pending that they want us to clear out. And I'll keep this screen on if you want to take a picture, if you want to scan it, if you want to just save it through a screenshot, anything works. But do keep in mind this offer is for 24 hours. It does not go beyond that. Tomorrow is the last date. So we'll be putting the link in the chat, but you won't be able to access it tomorrow. And the QR code gets invalid then as well. Sauritra, do we have any questions? Any queries?
For now, we're all set. It's just that Jim wanted AirPods as the surprise. So sorry for disappointing you, Jim. But I hope you liked what surprise we had for you.
Right. I'll just keep an eye on for a couple of more seconds. If anyone wants any question, anything that they want to discuss. I see a comment from David. Thanks, David. I really enjoyed your answers as well, and the way you were babysitting the model with us and like looking at the accuracy and seeing that it was already 85%. It like
It felt nice,
it felt nice that someone else does that too, because that's what we do 90% of our time, babysit models. Right, guys? So I think we are going to be signing off right now. Screen is visible for the last couple of seconds. Take a screenshot if you want to, take a picture, whatever. Cool. So I think that is it. We really enjoyed it. And thanks for coming in. Thanks for joining. We hope you go a long way in your deep learning journey. And yeah, that's it. Thank you.